Late at night, when the sky is clear and the air is calm, it can feel like space is full. The stars seem scattered everywhere, like glitter thrown across a black canvas. If you look long enough, you might notice a faint cloud of light stretching across the sky. That soft band is the Milky Way, our home galaxy, containing hundreds of billions of stars. From our point of view, the universe can appear crowded. But when astronomers step back and look at the universe on its largest scales, something surprising appears. The universe is not evenly filled with galaxies. Instead, it looks more like a giant foam, or perhaps a sponge. Imagine blowing bubbles in a sink full of soap. The bubbles press against each other, forming thin walls where the soap gathers. Inside each bubble, there is mostly empty space. Now imagine those bubbles not the size of coins, but millions of light years wide. A cosmic void is one of those bubbles. It is a vast region of space where very few galaxies exist. To understand just how big these regions are, it helps to think about the scale of a galaxy first. Our Milky Way galaxy is about 100,000 light years across. That means if you could travel at the speed of light, the fastest speed possible in the universe, it would still take 100,000 years just to cross from one side to the other. That distance is so enormous it's hard to picture. If the Milky Way were shrunk down to the size of a dinner plate, the solar system would be smaller than a grain of dust. Yet cosmic voids are not just a few galaxies wide. They are often hundreds of millions of light years across. That is like placing thousands of Milky Way galaxies side by side and still having empty space left over. So what exactly makes a region a void? It doesn't mean nothing exists there at all. Space almost never reaches perfect emptiness. Instead, a void simply means the area contains far fewer galaxies than normal. Imagine walking through a dense forest. Trees are everywhere around you. Trunks stand close together. Branches overlap, and sunlight struggles to reach the ground. Now imagine walking out of that forest into a giant open field. Suddenly, the trees are gone. Maybe there are a few scattered ones far away in the distance, but the land is mostly empty. Cosmic voids are like those enormous open fields of the universe. The galaxies are the trees, and the universe contains vast clearings where only a handful remain. This discovery surprised astronomers when they first started mapping the large-scale structure of the cosmos. For a long time, people assumed galaxies were spread somewhat evenly through space. Not perfectly even, of course, but roughly similar everywhere. But when better telescopes and sky surveys began charting millions of galaxies, a completely different pattern appeared. Galaxies gather together. They form long filaments, giant strands stretching across space like glowing threads. These filaments intersect and connect, forming enormous walls and clusters where galaxies crowd together. And between those structures lie the voids, huge regions where the number of galaxies suddenly drops. It's almost like looking at a three-dimensional spider web. The threads hold most of the matter, and between the threads are large, hollow spaces. Astronomers call this pattern the cosmic web. So why does the universe look like this? Why don't galaxies simply spread out evenly everywhere? That question leads us to one of the most important forces in the universe: gravity. Gravity pulls matter together. Over billions of years, regions that started slightly denser than others began attracting more and more material. Galaxies slowly gathered into clusters and long chains. As matter flowed into these dense areas, it left behind pockets where less and less material remained. Those pockets gradually became the cosmic voids. But how empty are they, really? If you were somehow floating deep inside one of these regions, what would you see? Would it look like complete darkness? Would there be any galaxies nearby? Or would the sky appear strangely quiet? The answer is both simple and fascinating. Even inside a cosmic void, space is not entirely empty. There might still be a few galaxies drifting through the darkness, sometimes separated by tens of millions of light years. To picture that distance, imagine shrinking Earth down to the size of a marble. On that same scale, the nearest star would still be thousands of kilometers away, about the distance between two countries. Now imagine galaxies spaced even farther apart than that. Inside voids, the universe becomes incredibly lonely. Galaxies that live there are often some of the most isolated objects known, and yet these enormous empty regions are not rare. In fact, cosmic voids are one of the main building blocks of the universe. They help shape the giant pattern that stretches across billions of light years. And when scientists map enough galaxies, the pattern becomes clear. Clusters, filaments, walls, and between them, enormous bubbles of emptiness. These voids can be so large that light itself takes hundreds of millions of years to cross them. If a beam of light began its journey on one side of a large void when dinosaurs still roamed Earth, that light might only be reaching the other side today. That thought alone raises an interesting question. If these massive empty regions exist all across the universe, could we be living inside one right now? It might sound unlikely at first. After all, the night sky above us seems filled with stars. But stars belong to our galaxy, and our galaxy is only one small island in an unimaginably vast cosmic ocean. So the real question becomes something much bigger. When we zoom far enough out, when we look at the universe on the largest possible scales, where exactly are we located inside this cosmic web? Are we sitting on one of the bright threads filled with galaxies? Or could we be drifting quietly inside one of the universe's giant bubbles of almost nothing? And if that were true, would we even notice? As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. When people first begin learning about the universe, one of the most surprising ideas is just how empty it really is. From Earth, the sky looks busy. On a clear night, you might see a few thousand stars with your eyes alone. With a small telescope, that number quickly grows into tens of thousands. With powerful observatories, astronomers can detect billions of galaxies, so it feels natural to imagine the universe as a crowded place. But that picture changes the moment we zoom out far enough. Imagine standing in a huge desert, not a small stretch of sand, but something as wide as an entire country. You walk for hours and see nothing but dunes. Occasionally, maybe once in a long while, you might find a small cluster of trees around a tiny oasis. Those rare green spots would feel incredibly special, simply because everything around them is empty. In many ways, that is what the large-scale universe looks like. Galaxies gather in clusters and long strands, but between them lie enormous regions where almost nothing exists. And these regions are not small. Some cosmic voids are hundreds of millions of light years wide. To picture that size, imagine driving across Earth from one side to the other. Even at highway speed, that trip would take days. Now imagine trying to cross something so large that light itself, moving at 300,000 kilometers per second, fast enough to circle Earth about 7 times in 1 second, would still need hundreds of millions of years to make the journey. That is the scale we are talking about. Now here comes the surprising part. When astronomers map the universe on these enormous scales, they find that these empty regions dominate the picture. In fact, cosmic voids may fill more than 80% of the universe's volume. 80%. Imagine a giant block of Swiss cheese sitting on a table. The cheese represents the matter in the universe: galaxies, gas, stars, and dark matter. But most of the block is actually holes. The holes are the voids. If you could shrink the entire universe down to the size of a football stadium, the galaxies would gather mostly along thin lines and walls around the edges. The center of the stadium would be mostly empty air. So why does the universe end up like this? Why does matter gather in some places, but leave others nearly empty? The answer again brings us back to gravity. Long ago, shortly after the universe began, matter was spread out in every direction. It wasn't perfectly smooth. Some areas had slightly more material, while others had slightly less. The differences were tiny. If you could measure them, they would be like small ripples on the surface of a calm lake. But gravity slowly amplified those ripples. Where there was a little extra matter, gravity pulled in more. Over billions of years, those regions grew denser and denser, forming the clusters and filaments where galaxies now gather. Meanwhile, the regions that started slightly emptier lost even more material. Matter flowed away from them toward the denser areas, and those regions slowly expanded into cosmic voids. It's a bit like what happens when people leave a crowded room. Imagine a large hall filled with hundreds of people. Suddenly, several exits open at the edges. People begin walking toward the doors. Over time, the center of the room becomes emptier and emptier, while the areas near the exits become crowded. Cosmic voids form in a similar way. Matter slowly flows away from them, leaving behind enormous pockets of emptiness. But what would it feel like to exist inside one? Would the universe look different? At first, you might think the night sky would look completely empty, but that isn't quite true. If you stood on a planet inside a galaxy located deep in a cosmic void, you would still see plenty of stars. Those stars belong to your own galaxy, so they would still fill the sky with familiar patterns. But when astronomers looked outward with powerful telescopes, something unusual would appear. There would be far fewer galaxies in the distance. Normally, when scientists point large telescopes toward deep space, they see galaxies everywhere. Images from space telescopes reveal thousands of galaxies in a patch of sky no larger than a grain of rice held at arm's length. Inside a deep cosmic void, that number might be dramatically smaller. Instead of seeing galaxies scattered across the sky like distant islands of light, the darkness between them would stretch much farther. The universe would feel quieter, lonelier. And yet, even though voids contain very little matter, they still play an important role in shaping the universe. In fact, some of the largest known structures in existence are not made of galaxies at all. They are made of emptiness. Imagine blowing soap bubbles again. The thin surfaces where the bubbles touch form delicate walls. Those walls outline the shapes of the bubbles themselves. Without the empty bubbles, the pattern would not exist. Cosmic voids work the same way. They define the structure of the cosmic web. The galaxies trace out the edges, but the voids create the enormous spaces in between. And this leads to another interesting question. If these giant bubbles of emptiness make up most of the universe, and if galaxies tend to sit along their edges, where exactly is our galaxy located? Are we close to the dense filaments where many galaxies gather? Or are we drifting somewhere deeper inside one of those vast cosmic bubbles? Astronomers have been asking this question for decades, because when scientists began studying the galaxies around us, they noticed something curious. The space near the Milky Way seemed a little less crowded than expected. Not completely empty, but perhaps slightly underfilled. And that small observation eventually led researchers to a fascinating idea. What if our galaxy isn't just near a cosmic void? What if we are living inside one? When we look up at the night sky, it's easy to feel like we are surrounded by stars in every direction. The Milky Way stretches across the darkness like a glowing river, and with a telescope, the universe quickly fills with countless distant galaxies. Because of this, most people naturally imagine that our galaxy sits in a fairly typical part of the universe, not especially crowded, not especially empty, just somewhere in the middle. But as astronomers began mapping the galaxies around us more carefully, something unusual started to appear. The region surrounding the Milky Way seemed a little quieter than expected. To understand what that means, it helps to imagine looking at a map of cities across a large country. Normally, cities and towns appear in clusters connected by highways. Some areas are busy and full of lights, while others have long stretches of open land. Now imagine zooming in on one region of that map and noticing something strange. The towns seem farther apart, the highways are fewer, and the open spaces between settlements stretch longer than usual. That is roughly what astronomers noticed when studying the nearby universe. Galaxies near the Milky Way seemed slightly less dense than the average found in other parts of the cosmos. Not empty, but not quite typical either. This observation led some scientists to ask a bold question. What if the Milky Way sits inside a large cosmic void? At first glance, the idea might sound strange. After all, our galaxy is part of a group of galaxies known as the local group. The local group contains about 50 galaxies, including the Milky Way, the Andromeda Galaxy, and many smaller dwarf galaxies. But the scale of a cosmic void is so enormous that even dozens of galaxies barely make a difference. To picture this, imagine a giant field stretching for hundreds of kilometers. Now scatter a few small houses across that land. Even though the houses exist, the field would still feel mostly empty. Cosmic voids are similar. They can contain galaxies, but those galaxies are spread extremely far apart. Astronomers began exploring this idea by studying how galaxies are distributed around us. They looked at their positions, their distances, and how many exist within certain regions of space. What they discovered was intriguing. In some directions, the number of galaxies seemed slightly lower than what the standard models of the universe predicted. So the natural question became, could this mean we live inside a large, underdense region of space? If we did, it would mean our galaxy is not located in a typical part of the cosmic web. Instead, we might be sitting inside one of its giant bubbles. And that possibility leads to another fascinating thought. If our galaxy really is inside a cosmic void, how big would that void need to be? The answer is enormous. Some researchers suggest that if such a void surrounds us, it could stretch hundreds of millions or even billions of light years across. That distance is almost impossible to imagine. If you could somehow travel across such a region at the speed of light, moving fast enough to circle Earth 7 times in a single second, the journey would still take longer than the entire history of human civilization. In fact, it would take longer than humans have existed as a species. So naturally, a question appears. If we were inside such a giant cosmic bubble, wouldn't it be obvious? Wouldn't the universe look dramatically different? Interestingly, the answer might be no, because even inside a large void, galaxies still exist. They are simply more spread out. From our position inside the Milky Way, we mostly see stars belonging to our own galaxy. Those stars fill the sky with familiar patterns like Orion, Cassiopeia, and the Big Dipper. These stars are relatively close, usually within a few thousand light years, compared to the distances between galaxies, which are often millions of light years apart. Those stars are practically in our backyard, so the night sky would still look beautiful and full. The real difference would only become noticeable when astronomers study galaxies far beyond our own. And that is exactly what scientists began doing. They started measuring how many galaxies exist at different distances from Earth. They looked in every direction, and they compared those measurements to what theories predicted. Some of those results hinted that our local region of space might be slightly less dense than average, but the picture is still debated. Some scientists think the difference is small and may simply be normal variation. After all, the universe is enormous, and no two regions are perfectly identical. Others believe the evidence could point toward a much larger structure, a vast cosmic void surrounding our galaxy. So how could we know for sure? One way is by studying how galaxies move. Gravity pulls galaxies towards dense regions. If our galaxy were inside a giant void, the surrounding galaxies might appear to drift outward, slowly moving away from the emptier region. Astronomers can measure these motions using precise observations of light, and those measurements might reveal whether our cosmic neighborhood is slightly underfilled. But there is another clue that scientists began noticing. When researchers looked very closely at the space around our solar system, they discovered something smaller, but still remarkable. Our local region of space appears to sit inside a bubble of unusually thin gas, a bubble hundreds of light years wide. This discovery would become known as something called the local bubble, and it raises an interesting possibility. If our solar system sits inside a small bubble, could our galaxy also sit inside a much larger one? Not all cosmic bubbles are unimaginably huge. Some are much closer to home. In fact, our own solar system appears to be sitting inside one right now. Astronomers call it the local bubble. At first, the name might make it sound small, but in space, even a local bubble can be enormous by everyday standards. The local bubble stretches for roughly 300 light-years across. To picture that distance, imagine a beam of light leaving Earth today. That light travels so fast, it could circle our planet 7 times in a single second. Yet even at that incredible speed, it would still take 300 years to cross this bubble from one side to the other. If human history were a road, the light would have started its trip around the time when Galileo was looking at the night sky through one of the first telescopes, and it would only now be reaching the other side. So what exactly is inside this bubble? Surprisingly, very little. Compared to many other parts of the Milky Way, the local bubble contains extremely thin gas. Space is always very empty, of course, even in denser regions between stars. There might be only a few atoms of gas in a space as large as a room, but inside the local bubble, the density drops even lower. It is like moving from a quiet countryside into a vast desert. There is still air there, but much less of it. Astronomers first noticed this unusual region while studying something called interstellar gas. This gas fills the spaces between stars inside galaxies. It is made mostly of hydrogen and helium, the same simple elements that make up stars themselves. When scientists observed nearby stars, they noticed something strange. The amount of gas between those stars and Earth seemed unusually low. It was as if our solar system sat inside a hollow pocket of space. Naturally, that raised an interesting question. How could such a bubble form? What could clear out a region hundreds of light years wide? The answer likely involves one of the most powerful events in the universe, a supernova. A supernova occurs when a massive star reaches the end of its life and explodes. In a single moment, that explosion can release as much energy as our sun will produce over its entire lifetime of about 10 billion years. That energy rushes outward as a powerful shockwave, pushing gas and dust away from the explosion. Imagine dropping a stone into a calm pond. Ripples spread outward in expanding circles. A supernova works in a somewhat similar way. The blast sweeps surrounding material outward, carving out a bubble in the interstellar gas. Now imagine not just one supernova, but many. Astronomers believe that the local bubble may have formed from a chain of supernova explosions that happened over millions of years. Several massive stars may have lived in our region of the galaxy long ago. When those stars reached the ends of their lives, they exploded one after another. Each explosion pushed gas farther away, gradually creating a large cavity. Over time, that cavity became the local bubble. Inside this bubble, the gas that remains is extremely hot, but incredibly thin. If you could somehow place a cube the size of a large room inside the local bubble and count the gas particles inside it, you might find only a handful, but is far emptier than most places in our galaxy. But here's something interesting. The local bubble is not completely alone. Astronomers have discovered that our bubble is connected to several other nearby bubbles, forming a kind of patchwork of cavities within the Milky Way. These bubbles are created by the same process, supernova explosions pushing material outward. Together, they shape the structure of the gas inside our galaxy. and the solar system happens to be drifting through one of them. But how did scientists actually discover this bubble? After all, we can't see it directly. The trick involves studying the light from distant stars. As light travels through space, it passes through interstellar gas. Certain elements absorb specific colors of light, leaving tiny fingerprints in the star's spectrum. By examining those fingerprints, astronomers can tell how much gas lies between us and the star. When they compared stars in different directions, they noticed something surprising. Within a few hundred light years, the amount of absorbing gas suddenly dropped. Beyond that distance, the gas became much thicker again. It was as if our solar system sat inside a hollow pocket, surrounded by denser walls, like living inside the center of a giant bubble. But here's the question that naturally comes to mind. If small bubbles like this can exist inside galaxies, could much larger bubbles exist on cosmic scales? And if our solar system sits inside a bubble created by ancient stellar explosions, could the Milky Way itself be located inside an even larger bubble in the universe? A bubble not hundreds of light years wide, but hundreds of millions, or even billions. Interestingly, some astronomers think the answer might be yes, because when they began mapping galaxies across enormous distances, they noticed hints of something unusual surrounding our cosmic neighborhood, a region that may stretch almost 2 billion light-years across, a region where galaxies appear slightly less common than expected. If that structure truly exists, it would be one of the largest cosmic voids ever suggested, and scientists have given it a name, the KBC void, a structure so vast that if you tried to drive across it at highway speed, the trip would take longer than the entire age of the universe, which raises a quiet but fascinating possibility. What if our galaxy is not just near a cosmic void, but deep inside one? As astronomers continued mapping the universe around us, they began noticing patterns that were difficult to ignore. Galaxies did not appear evenly spread in every direction. In some regions, they gathered into dense clusters and long glowing filaments. In others, the distances between galaxies seemed to stretch farther than expected. These observations slowly led to the idea that our cosmic neighborhood might sit inside a very large region with slightly fewer galaxies than average. This possible structure became known as the KBC void. The name comes from the scientists who studied it in detail: Ryan Keenan, Amy Barger, and Lennox Cowie. Using deep surveys of galaxies, they analyzed how many galaxies exist at different distances from Earth. Their results suggested something intriguing. The density of galaxies near the Milky Way might be lower than the average density found in the wider universe. In simple terms, our region might be a little emptier than normal. Not empty, like deep space between stars, of course. The Milky Way still belongs to a neighborhood of galaxies known as the local group, and beyond that lies a larger structure called the Virgo supercluster, which contains thousands of galaxies. But when astronomers measured galaxy density over much larger distances, they found a gradual increase. Closer regions seemed slightly underfilled. Farther regions appeared more crowded. This pattern raised a fascinating possibility. What if the Milky Way sits inside a giant cosmic void? If the KBC void exists as scientists describe it, its size would be truly staggering. Some estimates suggest it could be nearly 2 billion light-years across. That number is so large, it almost loses meaning, so it helps to picture it another way. Light travels incredibly fast, about 300,000 kilometers every second, fast enough to circle Earth 7 times in 1 second. Even at that speed, crossing a region 2 billion light-years wide would take 2 billion years. To put that in perspective, dinosaurs disappeared from Earth about 66 million years ago. That means light traveling across such a void would still have more than 30 times that journey left after passing the age of the dinosaurs. It would take longer than the time since the first animals began walking on land. Structures this large are difficult to imagine. If the Milky Way were shrunk down to the size of a grain of sand, a cosmic void like this would still be wider than an entire city. So naturally, scientists began asking an important question. How could such a massive void form? The answer again involves the slow work of gravity over billions of years. In the early universe, matter was not perfectly smooth. Some regions contained slightly more material than others. Those slightly denser areas began pulling matter inward. Galaxies formed and gathered into clusters. Filaments of matter stretched between them like glowing threads. Meanwhile, the slightly emptier regions lost more and more material. Matter slowly flowed away from them, pulled toward the denser areas. Over time, those emptier pockets grew larger and larger, like bubbles expanding inside rising bread dough. Eventually, they became the cosmic voids we see today. But the KBC void, if it exists as proposed, would be unusually large. Even among cosmic voids, a region approaching 2 billion light-years across would be enormous. That leads to another question. If we really live inside such a structure, how could astronomers tell? One method involves counting galaxies. Scientists measure how many galaxies appear within different distances from Earth. If our region is underdense, nearby volumes of space should contain fewer galaxies than regions farther away. Another method involves studying the brightness of distant objects, such as supernova explosions. These explosions act like cosmic flashbulbs. Because their brightness follows a predictable pattern, astronomers can use them to measure distances across the universe. If our galaxy sits inside a large void, the expansion of space might appear slightly different when measured from our location. That possibility has sparked lively debate among scientists. Some researchers find the evidence for the KBC void convincing. Others believe the observations can still be explained without requiring such a massive structure. After all, mapping the universe is an enormous challenge. Even with modern telescopes, astronomers are still piecing together the positions of millions of galaxies across unimaginable distances. It's a bit like trying to map an entire forest while standing among the trees. You can see the nearby trunks clearly, but understanding the full shape of the forest requires stepping far back. And stepping far back in the universe means looking billions of light years away. Despite the uncertainties, the idea of the KBC void remains one of the most intriguing possibilities about our cosmic location. Because if we truly sit inside a large, underdense region, it might influence something very important: our measurements of how fast the universe is expanding. That might sound surprising. After all, the expansion of the universe is a global process happening everywhere in space, but our local environment could still affect how we measure it. Imagine standing in a valley surrounded by hills. If you measured the wind from inside the valley, it might feel different compared to measurements taken on the open plains. In a similar way, living inside a giant cosmic void could subtly change what we observe when we look out at the universe. This idea leads to one of the most interesting puzzles in modern astronomy, a puzzle involving two different measurements of the universe's expansion rate that don't quite agree. Some scientists wonder whether our possible location inside a cosmic void might play a role. But before exploring that mystery, it helps to understand something else. Long before scientists began discussing the KBC void, astronomers had already discovered another giant bubble in the universe, a region so unexpectedly empty that it shocked the scientific community when it was first found. It would become known as one of the most famous voids ever discovered, the Boötes void, a region so empty that it earned a strange nickname: the Great Nothing. When scientists measure the universe, they are doing something remarkable. They are trying to understand the behavior of a structure so enormous that light itself needs billions of years to cross it. Every observation we make is like looking through a tiny window in an incredibly vast landscape. Because of this, our location inside the universe matters. It's a little like trying to understand the shape of an entire forest while standing somewhere inside it. If you happen to stand in a dense patch of trees, the forest might feel crowded. If you stand in a clearing, it might feel open and spacious. Both experiences are real, but neither tells the full story by itself. Astronomers face a similar challenge when measuring one of the most important properties of the universe: how fast it is expanding. For nearly a century, scientists have known that the universe is growing larger over time. Galaxies are slowly drifting away from each other as space itself stretches. This discovery was first made by observing distant galaxies whose light appears slightly shifted toward the red end of the spectrum. This effect, known as redshift, happens because the wavelength of light stretches as the universe expands. You can picture it like a rubber band. If you draw small dots on the rubber band and then pull it, the dots move farther apart as the band stretches. The farther apart the dots are, the faster they seem to move away from each other. Space behaves in a similar way. Galaxies that are farther away appear to move away faster than galaxies nearby. Scientists describe this relationship using a number called the Hubble constant. The Hubble constant tells us how quickly the universe is expanding. It's a bit like measuring how fast the dots on the rubber band move apart as the band stretches. But here's where things become interesting. Different methods of measuring the expansion of the universe give slightly different answers. Some measurements suggest the universe is expanding faster. Others suggest it is expanding a little slower. The difference might not sound large, but in science, even a small mismatch can be important. Imagine two clocks that should show the same time but differ by a few minutes. That small difference might reveal that something about the system is not fully understood. Astronomers call this puzzle the Hubble tension. And one possible explanation involves cosmic voids. So how could living inside a void change what we measure? To understand this, imagine standing inside a large, shallow valley surrounded by hills. Rainwater falling on the hills tends to flow downward toward the lower areas. If you were standing in the valley and measuring the flow of water around you, the pattern might look different than it would from the top of one of the hills. In the universe, matter tends to flow toward dense regions like galaxy clusters. Meanwhile, regions that are less dense, like cosmic voids, slowly expand as matter drifts away from them. If our galaxy were inside a large void, the surrounding galaxies might appear to move outward slightly faster than average. From our point of view, it could look as though the universe is expanding more quickly nearby. That effect might influence how we calculate the Hubble constant. In other words, our local environment might slightly change what we observe. It would be similar to measuring the speed of cars on a highway while standing on a downhill slope. Cars might naturally move faster there compared to a flat road, even though the highway itself follows the same rules everywhere. Of course, this idea remains under careful study. Some scientists think that a large local void could explain part of the Hubble tension. Others believe the effect would not be strong enough to fully solve the puzzle. But the possibility itself highlights something fascinating. Our location inside the universe is not necessarily average. We observe everything from a single point inside a vast cosmic structure. And that structure may contain filaments, clusters, and enormous empty bubbles. If we happen to live inside one of those bubbles, it could subtly influence the measurements we make. Astronomers are continuing to study this idea by mapping galaxies across ever larger regions of space. New telescopes and sky surveys are collecting detailed information about millions of galaxies, allowing scientists to trace the cosmic web more clearly than ever before. These maps reveal the long filaments of galaxies and the wide voids between them. When seen together, the universe begins to resemble something almost organic, like a network of cells, or the delicate foam formed by soap bubbles pressed together. But the discovery of cosmic voids did not begin with the KBC void or modern galaxy surveys. Long before that, astronomers stumbled upon something unexpected while studying galaxies in one particular part of the sky. They found a region so strangely empty that it seemed almost impossible a vast volume of space where galaxies were nearly absent. When the discovery was announced, it surprised scientists around the world because this region was not just slightly underfilled, it was enormous, so large that if the Milky Way sat inside it, the nearest galaxies might be hundreds of millions of light years away. This mysterious region would become one of the most famous cosmic voids ever discovered, a place so empty that astronomers gave it a simple, unforgettable nickname, the Great Nothing. In the early days of modern astronomy, scientists were still learning how galaxies are arranged across the universe. Telescopes had already revealed that the Milky Way was not alone. There were countless other galaxies scattered through space, each one containing billions or even trillions of stars. But exactly how those galaxies were distributed was still a mystery. Were they spread out evenly? Did they cluster together randomly? Or did they form some kind of pattern? To answer these questions, astronomers began carefully mapping the positions of galaxies across the sky. This work was slow and patient. Each galaxy had to be observed, its light studied, and its distance measured. Only then could it be placed on a three-dimensional map of the universe. Imagine trying to map every city in a massive country while standing inside it. You would need to measure how far away each city is, and in which direction it lies. That is essentially what astronomers were doing with galaxies. As these maps slowly grew, scientists began to notice something unexpected. Galaxies did not appear scattered randomly. Instead, they gathered into clusters and chains, leaving behind wide empty spaces in between. At first, those empty spaces were thought to be small gaps, but in 1981, a discovery changed everything. Astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman were studying galaxies in the direction of a constellation called Boötes. Boötes is not a particularly famous constellation. If you look at it in the night sky, it forms a simple kite-like shape. It sits near the bright orange star Arcturus, one of the most noticeable stars visible from Earth. But what those astronomers discovered in that direction had nothing to do with stars. It had to do with what wasn't there. As they measured the distances to galaxies in that region, they realized that a huge volume of space contained almost none at all. It wasn't just a small patch. It was massive. The region appeared to stretch roughly 330 million light-years across. That number may sound abstract, so it helps to picture it another way. Light travels incredibly fast, fast enough to circle Earth 7 times in a single second. Even so, crossing a region 330 million light-years wide would take 330 million years. To put that into perspective, when light began traveling across that distance, dinosaurs were still roaming Earth. The continents looked different. Flowers had barely evolved, and humans would not appear for another hundreds of millions of years. That is the scale of the emptiness astronomers discovered, a region so large that if our entire Milky Way galaxy were placed inside it, the galaxy would appear like a tiny speck floating in an enormous dark room. Naturally, the discovery caused excitement and a bit of disbelief. Could such a huge empty space really exist? Or was it simply a gap in the observations? At first, scientists were cautious. The maps of galaxies at the time were still incomplete, and it was possible that hidden galaxies simply hadn't been detected yet. But as more observations were made, the picture became clearer. The region truly contained very few galaxies. Not zero, but far fewer than expected for a region that size. This giant empty bubble became known as the Boötes void. Some scientists even began calling it something more dramatic: the Great Nothing. The name captured the strange feeling of the discovery. After all, space is already mostly empty, yet here was a region where the emptiness itself seemed to dominate. But even inside this vast cosmic bubble, the universe had not completely abandoned it. A small number of galaxies still existed within the void. They were extremely isolated, separated by huge distances. Imagine standing on a tiny island in the middle of a massive ocean. You might see another island far away on the horizon, but the water between them stretches endlessly. Galaxies inside the Boötes void live in a similar situation. They are some of the loneliest galaxies known, and their existence raises a fascinating question. How did such a huge empty region form in the first place? Once again, gravity provides the answer. In the early universe, matter began clumping together under the pull of gravity. Slightly denser regions attracted more and more material. As galaxies formed and gathered into clusters, the surrounding regions lost matter. Those emptier regions slowly expanded. Over billions of years, the difference between dense regions and empty regions grew larger and larger. The cosmic web began to take shape. Filaments of galaxies formed long glowing threads. Walls of galaxies surrounded enormous bubbles, and inside those bubbles lay the voids. The Boötes void became one of the first clear examples of this structure. It showed astronomers that the universe was not just a random scatter of galaxies. It had a pattern, a giant foam-like structure stretching across unimaginable distances. And the Boötes void was one of the biggest holes in that cosmic foam ever discovered at the time. But this discovery raised another interesting thought. If astronomers could accidentally stumble upon such a massive empty region, how many more might exist across the universe? And if the Boötes void already seemed enormous, could there be voids even larger still? As telescopes improved and galaxy surveys expanded, scientists began mapping larger and larger volumes of space. What they found would reveal that the Boötes void was not unique. In fact, the universe contains many enormous voids, some so large that they rival the biggest structures known in existence. But the Boötes void itself remained shocking for another reason. Because when scientists first calculated how empty it was, the numbers were hard to believe. When astronomers first realized how large the Boötes void was, the size alone was already astonishing. A region 330 million light-years across is difficult to imagine. If light began crossing it when the first dinosaurs appeared on Earth, that light would only now be reaching the other side. But the real surprise was not just its size, it was how few galaxies lived inside it. When scientists estimate how many galaxies should exist within a region of space, they rely on what they see in other parts of the universe. If you look at a typical volume of space large enough to contain hundreds of millions of light-years, you would normally expect thousands of galaxies. Some might be large spirals like the Milky Way. Others might be giant elliptical galaxies containing trillions of stars. And many would be smaller dwarf galaxies, faint and scattered, but still present. But inside the Boötes void, astronomers initially found only a few dozen galaxies. To understand how strange that is, imagine flying over a continent at night. Normally, you would see countless city lights scattered across the land. Even in rural areas, towns appear every so often. Now imagine flying over a region as wide as an entire country and seeing only a handful of lights, just a few isolated towns, separated by huge stretches of darkness. That is roughly what the Boötes void looked like when astronomers mapped it. It was as if the universe had simply skipped filling that area. Naturally, this discovery made scientists wonder if something unusual had happened there. Could a gigantic explosion have cleared out the galaxies? Could powerful forces have pushed matter away? Or was it simply the natural result of the universe's large-scale structure? Over time, as astronomers studied the cosmic web more carefully, the answer became clearer. The Boötes void was not created by a violent event. Instead, it likely formed slowly over billions of years. To picture how this works, imagine a large sheet of dough with raisins scattered inside it. As the dough rises in the oven, it expands in every direction. The raisins move apart as the dough stretches. But some areas of the dough might contain more raisins than others. As the dough expands, those clusters of raisins remain relatively close together. Meanwhile, the areas with fewer raisins grow larger and emptier. In the universe, galaxies play the role of raisins, while space itself stretches over time. Gravity pulls galaxies toward dense regions, forming clusters and filaments. As this happens, the emptier regions expand into large bubbles, the cosmic voids. The Boötes void likely grew this way. Matter gradually flowed toward nearby galaxy clusters, leaving behind a giant pocket of space with very little material. Over billions of years, the pocket expanded and became emptier. But even within this enormous bubble, a few galaxies still managed to exist. And those galaxies turned out to be very interesting, because galaxies inside voids often look different from galaxies inside crowded clusters. In dense regions of the universe, galaxies frequently interact with each other. They pass close by, pull on each other with gravity, and sometimes even collide. These interactions can trigger bursts of star formation or distort the shapes of galaxies. Inside a void, things are much quieter. Galaxies there are often isolated. They drift through space with few neighbors nearby. Some astronomers compare them to small villages far away from busy cities. Life in those villages moves at a slower pace. In the same way, galaxies inside voids often evolve more slowly. They may form stars steadily over long periods, undisturbed by frequent collisions. Studying these lonely galaxies helps scientists understand how galaxies grow when left mostly alone. But the Boötes void also taught astronomers something even bigger. It confirmed that the universe has a large-scale pattern. Galaxies gather into walls and filaments that surround giant bubbles of emptiness. And those bubbles can be unimaginably large. If you could somehow stand in the middle of the Boötes void and look outward with a powerful telescope, the nearest large galaxy clusters might appear hundreds of millions of light years away. The universe would feel incredibly spacious, yet even that vast emptiness is part of the cosmic web, like the hollow spaces between the strands of a spider's web. The Boötes void was one of the first clear examples of this pattern. But as galaxy surveys improved and astronomers mapped larger portions of the sky, they began discovering many more voids. Some were similar in size to the Boötes void, others were even larger. And this discovery led scientists to imagine something fascinating. If a galaxy happened to live deep inside one of these giant bubbles, what would its night sky look like? Would observers there see a universe filled with distant galaxies? Or would the sky appear strangely quiet compared to what we see from Earth? Because the appearance of the cosmos might change depending on where you are located inside the cosmic web. And if a galaxy were sitting near the center of a massive void, the view of the universe could be very different indeed. When we step outside on a clear night and look up, the sky feels rich with light. Thousands of stars sparkle above us. Some shine brightly. Others appear faint and distant. If the sky is dark enough, we can even see the pale band of the Milky Way stretching across the sky like a soft river of light. But almost everything we see with our eyes belongs to our own galaxy. The Milky Way contains hundreds of billions of stars, spread across a disk about 100,000 light years wide. If that disk were shrunk down to the size of a large dinner plate, the solar system would be smaller than a grain of dust somewhere near the middle. So when we look at the night sky, we are mostly seeing our local neighborhood inside this enormous galaxy. The other galaxies of the universe are much farther away. Even the Andromeda Galaxy, the nearest large galaxy to us, is about 2.5 million light-years away. Light leaving Andromeda tonight will not reach Earth until long after every human alive today is gone. Because of that distance, Andromeda appears only as a faint smudge in the sky. Now imagine standing on a planet inside a galaxy that sits deep inside a cosmic void. Would the sky look different? At first, it might not. The stars of that galaxy would still fill the sky just as the stars of the Milky Way fill ours. Constellations would still exist. Nebulae would glow softly. Star clusters would sparkle like tiny jewels. From the surface of that planet, the sky would feel familiar. But the real difference would appear when astronomers there began looking outward with powerful telescopes. Here on Earth, when scientists aim large telescopes at deep space, they often see galaxies everywhere. Some telescope images show thousands of galaxies in a patch of sky no larger than a grain of rice, held at arm's length. It is like looking across a vast ocean filled with distant islands of light. But inside a large cosmic void, that picture could change. The galaxies beyond the local one would be much farther apart. Instead of seeing many galaxies scattered across the sky, astronomers might see only a few faint ones, separated by wide stretches of darkness. The cosmic ocean would still exist, but the islands would be much harder to find. To picture this difference, imagine two beaches at night. One beach faces a busy coastline filled with towns and cities. From the shore, you can see lights dotting the horizon everywhere. The other beach faces a remote stretch of ocean, with almost no settlements for hundreds of kilometers. From that shore, the horizon would look mostly dark. Both beaches exist on the same planet, but their views feel very different. In the same way, galaxies inside cosmic voids might see a quieter universe. Another difference could appear when mapping the large-scale structure of galaxies. Astronomers on Earth observe galaxies arranged in long filaments and clusters. These structures form the cosmic web, the enormous network connecting galaxies across billions of light years. But observers deep inside a void might initially see fewer nearby structures. The nearest dense clusters might lie hundreds of millions of light years away. That is like living in a small village surrounded by enormous empty plains before reaching the nearest city. And this raises an interesting question. If observers lived deep inside such a void, would they realize it? Or would they assume their region was normal? The answer might not be obvious, because from any one location in the universe, we can only see part of the cosmic web. It takes enormous galaxy surveys to reveal the full structure. Astronomers must measure the positions and distances of millions of galaxies before the pattern becomes clear. Without those large maps, a void might simply appear as a quiet region of space. But there is another subtle effect that living inside a void might create. It could influence how distant galaxies appear to move. Because voids slowly expand as matter flows away from them, galaxies near the edges might drift outward. Observers inside the void could see surrounding galaxies gradually moving away in every direction. From their perspective, the universe might appear to expand slightly faster nearby. That idea connects back to the puzzle scientists are still studying today. If our galaxy sits inside a large, underdense region, it might slightly affect the expansion measurements we observe. But the visual experience of living inside a void would still contain beauty. Even in the emptiest regions of the universe, galaxies shine with billions of stars, nebulae glow with colorful clouds of gas, and the deep black sky would still stretch endlessly overhead. In fact, some of the most isolated galaxies discovered by astronomers live inside cosmic voids. These galaxies drift almost alone through vast spaces, separated from their nearest neighbors by tens of millions of light years. To picture that distance, imagine driving across a continent. Now imagine driving across thousands of continents, placed end to end, without encountering another city. That is roughly the isolation some of these galaxies experience. They are the loneliest galaxies known. Yet even these quiet regions are part of the cosmic web. And as astronomers continued exploring the universe, they began discovering voids even larger than the Boötes void. Some stretched across hundreds of millions of light years. Others seemed even more extreme. These discoveries revealed that cosmic voids are not rare accidents. They are a fundamental part of the universe's structure. In fact, some of the largest structures ever discovered in the cosmos are not made of matter at all. They are made of space that is almost completely empty. Once astronomers realized that enormous empty regions like the Boötes void could exist, A natural question followed. Was it unique? Or were there many more like it scattered across the universe? To find out, scientists needed something very powerful. Not a single telescope, not even a few. They needed maps of millions of galaxies. Mapping galaxies across space is a bit like building a three-dimensional map of cities across an entire planet. It requires measuring not only where each galaxy appears in the sky, but also how far away it is. Astronomers determine those distances by studying the light from galaxies. As the universe expands, the light from distant galaxies stretches toward redder wavelengths. By measuring this stretching, scientists can estimate how far the light has traveled. Each galaxy becomes a small point on a massive cosmic map. As these points accumulate by the millions, a giant picture begins to emerge, and that picture revealed something remarkable. The Boötes void was not an odd exception. The universe is filled with giant voids. Some are similar in size to the Boötes void, others are much larger. Many cosmic voids stretch hundreds of millions of light years across. To understand that size, imagine traveling across such a region at the speed of light, even moving fast enough to circle Earth 7 times in a single second. It would still take hundreds of millions of years to reach the other side. That journey would last longer than the entire time dinosaurs lived on Earth. These enormous voids appear throughout the cosmic web, like bubbles packed together inside foam. The galaxies form the thin walls and filaments around the edges of these bubbles. Inside the bubbles themselves, galaxies become rare. One of the fascinating things about cosmic voids is their variety. Some are nearly spherical, resembling giant cosmic balloons. Others are stretched and irregular, shaped by the surrounding filaments of galaxies. Their boundaries are not sharp like the walls of a room. Instead, the density of galaxies gradually increases as you move from the center of a void toward its edges. Imagine walking across a huge open field toward a forest. At first, the land feels empty. Then a few trees begin appearing here and there. Eventually, the trees become dense and the forest surrounds you. Cosmic voids behave in a similar way. The centers are the emptiest regions. Closer to the edges, galaxies become more common, but the true scale of these structures can be difficult to grasp. If a cosmic void were placed next to the Milky Way galaxy, the comparison would be staggering. The Milky Way is about 100,000 light-years across. A large void might be 300 million light-years wide. That means you could place the Milky Way galaxy 3,000 times across the diameter of the void. It would be like placing a small pebble inside a massive stadium. And yet, these structures are only part of an even larger pattern, because the cosmic web itself stretches across billions of light-years. When astronomers map enough galaxies, the universe begins to resemble something very familiar: foam, or a sponge, or even a network of soap bubbles pressed together. Each bubble represents a void. The thin surfaces where bubbles touch represent the filaments of galaxies. The pattern repeats again and again across space, and the more galaxies scientists map, the clearer this pattern becomes. Modern galaxy surveys have revealed hundreds of cosmic voids across the observable universe. Some surveys examine millions of galaxies at once, creating detailed maps that stretch billions of light years in every direction. These maps are among the largest scientific projects ever attempted. If printed on paper, some of these galaxy maps would stretch across entire rooms, but instead of cities or roads, they contain tiny dots representing galaxies millions of light years apart. From these maps, astronomers can measure the size, shape, and distribution of cosmic voids. And they have discovered that voids are not just empty gaps between galaxies. They are a fundamental part of how the universe is organized. In fact, voids make up most of the universe's volume. Galaxies, despite their immense numbers, occupy only a small fraction of the total space. Imagine filling a giant container with soap bubbles. Most of the container would be air trapped inside the bubbles. Only thin layers of soap would form the bubble walls. The universe works in a similar way. Most of the cosmic volume lies inside the voids. The galaxies gather along the thin structures between them. But even among these giant empty regions, some voids stand out for their extraordinary size. One of the most intriguing examples lies in a distant part of the sky, associated with a strange cold patch in the early light of the universe, a region where the cosmic background radiation appears slightly cooler than the surrounding areas. Astronomers began investigating whether a giant void might exist there, and the results pointed towards something astonishing. A structure so vast that it might stretch hundreds of millions, or even nearly 1 billion light-years across. If confirmed, it would rank among the largest cosmic voids ever discovered. This mysterious region is known as the Eridanus supervoid, and it may be connected to one of the strangest features ever observed in the ancient light left over from the birth of the universe. Long before galaxies and stars filled the universe, space looked very different. About 13.8 billion years ago, the universe was extremely hot and dense. Matter and energy were packed together so tightly that light itself could not travel freely. Imagine trying to see through thick fog. Light scatters in every direction, and nothing appears clearly. The early universe was similar, but much hotter and far more crowded. Then something important happened. As the universe expanded, it slowly cooled. After about 380,000 years, space became cool enough for light to finally travel freely across the cosmos. That ancient light still exists today. Astronomers call it the cosmic microwave background, often shortened to CMB. You can think of it as the oldest photograph of the universe. If we could shrink the entire observable universe down to the size of Earth, this ancient light would form a glowing shell surrounding us in every direction. But it is not perfectly smooth. Tiny temperature differences appear across the sky. Some regions are slightly warmer, others slightly cooler. These differences are incredibly small. Most variations are only about 1 part in 100,000. To picture that, imagine a pot of water heated to exactly 100 degrees. A difference of 1 part in 100,000 would be like the temperature changing by only 0.01 degrees, far smaller than what a normal thermometer could detect. Yet with sensitive instruments, scientists can measure these tiny variations across the sky, and those variations reveal something important. They show the small ripples in matter that later grew into galaxies, clusters, and cosmic voids. But when astronomers studied the cosmic microwave background in detail, they noticed something unusual. One region of the sky appeared significantly colder than the surrounding areas. This region became known as the cosmic cold spot. The cold spot lies in the direction of a constellation called Eridanus, a long, winding pattern of stars that stretches across the southern sky. On maps of the cosmic microwave background, the cold spot looks like a faint circular patch, slightly darker than the surrounding areas. At first glance, it might not seem dramatic, but its size makes it remarkable. The cold spot spans about 5 degrees across the sky. To picture that, hold your hand out at arm's length. Your fist covers roughly 10 degrees of the sky. That means the cold spot covers an area about half the width of your fist. But that patch is incredibly far away. The cosmic microwave background comes from light that has been traveling for nearly 13.8 billion years. So the cold spot represents a huge region of space in the early universe. Naturally, scientists began wondering what could cause such a large temperature difference. One possible explanation involves cosmic voids. Here's how that might work. As the ancient light of the cosmic microwave background travels across the universe toward us, it passes through galaxies, clusters, and voids along the way. Gravity slightly changes the energy of that light. When light falls into a region filled with matter, gravity pulls it inward, giving it a small boost of energy. As the light climbs back out, it loses that energy again. But if the universe is expanding, which it is, the situation becomes a little more complicated. In expanding space, light passing through a large cosmic void can lose a tiny bit of extra energy. That makes the light appear slightly cooler when we detect it. So astronomers began asking an intriguing question. What if the cold spot exists because the ancient light passed through a massive cosmic void on its way to Earth? If such a void existed, it would need to be enormous, much larger than the Boötes void, possibly stretching hundreds of millions of light years across. Scientists began searching for evidence of such a structure in the direction of the cold spot, and over time, observations suggested that a large underdense region of galaxies might indeed exist there. This region became known as the Eridanus supervoid, but the scale of this possible void is extraordinary. Some studies suggest it could span nearly 1 billion light years. To picture that distance, imagine light beginning its journey across the void when the first animals began walking on land, around 400 million years ago. Even traveling at the fastest speed possible in the universe, that light might still not have finished crossing the void today. Structures this large challenge our sense of scale. If the Milky Way were the size of a coin, 1 billion light-year wide void would be larger than an entire city. And yet such immense structures may exist within the cosmic web. However, the story of the cold spot is still under investigation. Some scientists believe the Eridanus supervoid could explain part of the temperature difference. Others think the cold spot may have formed in the early universe itself, unrelated to any nearby structure. The truth may involve a combination of factors, but regardless of the final explanation, the search for the Eridanus supervoid has revealed something important. The universe contains structures of staggering size. Some are built from enormous clusters of galaxies. Others are formed by vast regions where galaxies are scarce, and these giant cosmic bubbles are not isolated. When astronomers map large portions of the sky, they begin finding hundreds of voids, each one part of the greater cosmic web. The more we explore, the more the universe begins to resemble something unexpected. Not a uniform spread of galaxies, but a vast foam of matter and emptiness woven together across unimaginable distances. And some of the largest bubbles in that cosmic foam may stretch close to 1 billion light years across. When astronomers first began studying cosmic voids, regions like the Boötes void already felt enormous. A bubble of space, 330 million light years across, seemed almost beyond imagination. But as scientists continued mapping the universe in greater detail, they discovered something even more surprising. Some voids may be far larger. One of the most intriguing examples is the possible structure connected to the Eridanus supervoid. If measurements are correct, this region may stretch close to 1 billion light years across. That distance is almost impossible to picture. Light moves incredibly fast, about 300,000 kilometers every second. In the time it takes you to blink, light could circle the entire Earth several times. Yet even traveling that fast, crossing a region 1 billion light years wide, would take 1 billion years. To understand how long that is, imagine starting the journey when the earliest complex life began appearing in Earth's oceans roughly 600 million years ago. Light traveling across such a void would still not have reached the other side today. That is the kind of scale astronomers are dealing with. Structures so large that their dimensions stretch across a noticeable fraction of the observable universe. So how could a void grow this big? The answer again lies in the slow movement of matter over billions of years. In the early universe, tiny variations in density existed everywhere. Some regions contained slightly more matter than others. The differences were incredibly small, less than 1 part in 100,000. But gravity slowly amplified those tiny differences. Regions with more matter attracted additional material. Over time, galaxies gathered into clusters and filaments. Meanwhile, the slightly emptier regions lost matter. Material drifted away from them, pulled toward the denser structures nearby. Those emptier areas gradually expanded. Imagine stretching a sponge made of soft foam. As the foam expands, the holes inside it grow larger. The material collects along the thin walls between those holes. The universe behaves in a somewhat similar way. The filaments of galaxies form the foam-like walls. The voids become the expanding holes between them. Over billions of years, some of those holes can grow very large, but a void approaching 1 billion light-years across pushes the limits of what scientists once thought possible. To understand the scale, imagine placing galaxies across that distance. The Milky Way is about 100,000 light-years wide. If you placed one Milky Way galaxy after another in a straight line, you would need 10,000 galaxies just to span 1 billion light-years. That is like lining up thousands of cities across an entire continent. And yet, inside a giant cosmic void, those galaxies are mostly missing. Instead of thousands of galaxies filling the space, only a small number might exist, scattered across vast distances. Some of those galaxies could be separated by tens of millions of light-years. To picture that distance, imagine driving from one side of Earth to the other. Even at highway speed, that journey would take several days. Now imagine repeating that trip millions of times before reaching the next galaxy. That is the level of isolation some galaxies experience inside large voids. But how do astronomers detect such enormous structures? After all, a void is defined by the absence of galaxies. To find one, scientists must first map the positions of huge numbers of galaxies across the sky. Large surveys measure the distances to millions of galaxies and place them on three-dimensional maps of the universe. When those maps are viewed together, patterns begin to appear. Galaxies form long chains. Clusters gather at the intersections of those chains, and between them lie enormous gaps. By studying these patterns, astronomers can identify the boundaries of cosmic voids. It is a bit like mapping a forest from the air. If you fly over a landscape filled with trees, clearings will appear where the trees are missing. By measuring the size of those clearings, you can determine the shape of the forest. Cosmic voids are the clearings of the universe. And when astronomers began mapping the region around the Eridanus cold spot, they found evidence that a large underdense region of galaxies might exist there. However, the exact size and shape of the Eridanus supervoid are still being studied. Some measurements suggest it may be slightly smaller than 1 billion light-years. Others suggest it could extend even farther, but even the lower estimates place it among the largest voids ever identified. Discoveries like this reveal just how dramatic the universe's large-scale structure can be. Galaxies are not sprinkled randomly across space like grains of sand. Instead, they form an enormous network of filaments and clusters surrounding giant bubbles of emptiness. And the more galaxies scientists map, the clearer that network becomes. In fact, one of the most important projects in modern astronomy created a map so large and detailed that it transformed our understanding of the cosmic web. This project surveyed hundreds of thousands of galaxies across a huge portion of the sky. When astronomers looked at the results, the universe suddenly revealed its hidden pattern, a pattern filled with filaments, walls, clusters, and hundreds of enormous voids scattered throughout the cosmos. To truly understand the universe, astronomers needed a map, not a small one. Not a map showing a few thousand galaxies. They needed something far larger, a map containing hundreds of thousands, even millions of galaxies spread across enormous distances. Creating such a map was not simple. Each galaxy had to be observed, its light measured, and its distance estimated. Only then could it be placed correctly in three-dimensional space. This challenge led to one of the most ambitious projects in modern astronomy, the Sloan Digital Sky Survey, often called SDSS. Instead of studying just a few galaxies at a time, this survey used powerful telescopes and special instruments to measure the positions and distances of huge numbers of galaxies across the sky. Imagine trying to map every city across an entire continent. Now imagine doing the same thing for galaxies separated by millions or billions of light years. That is what the Sloan survey attempted. Over many years, it collected detailed information about hundreds of thousands of galaxies, eventually growing into maps containing millions. Each galaxy became a tiny glowing point in an enormous cosmic chart. When astronomers first looked at these maps, the pattern that appeared was breathtaking. Galaxies were not scattered randomly. They formed long filaments, like glowing strands stretching across space. Where these filaments crossed, galaxy clusters formed, dense regions filled with hundreds or thousands of galaxies packed together. Between these structures were the voids, huge bubbles of space where galaxies were scarce. Some voids appeared similar in size to the Boötes void. Others were even larger. When the Sloan survey data was analyzed, scientists identified hundreds of cosmic voids across the observed portion of the universe. Some of these voids stretched 200 million to 400 million light-years across. To picture that size, imagine light starting its journey across one of these voids when the first dinosaurs appeared around 230 million years ago, even traveling at the fastest speed possible in the universe. That light would still not have reached the other side today. That is the scale of these structures. And yet, when you zoom out far enough on the cosmic map, the pattern begins to look strangely familiar. Many scientists compare it to foam. If you look closely at soap bubbles pressed together in a sink, you'll notice that the bubbles form a network of thin walls surrounding empty spaces. The walls are where the soap gathers. The bubbles themselves are mostly air. The universe looks similar. The filaments of galaxies form the thin walls. The voids become the enormous bubbles between them. Another way to picture it is to imagine a sponge. A sponge contains solid material forming a network of thin surfaces, while the holes between those surfaces hold mostly empty space. If you could zoom out far enough, the universe might look like a cosmic sponge stretching across billions of light years. This idea was once difficult to accept. For a long time, scientists expected galaxies to be spread out more smoothly, but the Sloan Digital Sky Survey showed that the universe has a clear, large-scale structure. Clusters, filaments, and voids appear again and again across the cosmic map. And the voids themselves are not random holes. They follow patterns shaped by gravity and the distribution of matter in the early universe. In fact, some of the most impressive images created by astronomers come from these three-dimensional galaxy maps. When viewed from the side, the map sometimes resembles a slice through a giant loaf of bread filled with raisins. The raisins represent galaxies, but they do not fill the loaf evenly. Instead, they form walls and strands surrounding enormous gaps. Those gaps are the cosmic voids. Another interesting discovery from the Sloan survey is that voids are not completely empty. Even in the emptiest regions, a few galaxies still appear. These galaxies often have unusual properties. They tend to be smaller, less crowded, and sometimes rich in gas, meaning they still have plenty of material available to form new stars. Without frequent interactions with other galaxies, they evolve in relative isolation. It is a bit like living in a remote village, far from busy cities. Life moves more quietly. Changes happen slowly. Studying these galaxies helps astronomers understand how galaxies develop when they are not constantly influenced by nearby neighbors. But perhaps the most important lesson from the Sloan Digital Sky Survey was simply this: the universe has a shape, not a rigid shape like a solid object, but a pattern, a giant network of matter stretching across space, and the voids are just as important to that pattern as the galaxies themselves. Without the empty bubbles, the cosmic web would not exist. The filaments and clusters are defined by the spaces around them. The emptiness gives the structure its form. When scientists visualize these maps, the universe begins to resemble something delicate and intricate, a vast foam of light and darkness woven together across unimaginable distances. Galaxies glowing along thin strands, and enormous hollow bubbles stretching between them. This pattern appears again and again as more galaxies are mapped, and the deeper astronomers look into space, the more clearly the cosmic web reveals itself, a universe that is not evenly filled with matter, but shaped by vast bubbles of emptiness, surrounded by rivers of galaxies. When astronomers first began mapping galaxies in 3 dimensions, the results were surprising. For a long time, people imagined the universe as something fairly simple. Galaxies scattered across space somewhat evenly, like grains of sand spread across a beach. But when enough galaxies were mapped together, a completely different picture appeared. Instead of randomness, there was structure, and not just small structures like galaxy groups or clusters. There was a pattern stretching across hundreds of millions and even billions of light years. When scientists visualized the positions of galaxies in large surveys, they noticed something striking. Galaxies gathered along long filaments, thin strands of matter stretching through space. These filaments connected massive clusters of galaxies, forming intersections that looked like glowing knots in the network. And between those strands were enormous empty regions, the cosmic voids. When viewed together, the pattern looked remarkably similar to something we see in everyday life: a sponge. If you hold a sponge in your hand and look closely, you'll notice it is full of holes. The solid material forms thin surfaces and strands surrounding those holes. Most of the sponge is actually empty space. Only a small portion is the material itself. The universe appears to have a similar structure. The galaxies and clusters form the thin framework. The voids become the giant holes between them. Another comparison many scientists like to use is soap bubbles. When bubbles press against each other in foam, they create delicate walls that outline the shape of each bubble. The bubbles themselves contain mostly air. The universe resembles a cosmic foam of galaxies and emptiness. Each void is like a giant bubble. The filaments of galaxies form the thin surfaces between those bubbles, and the pattern repeats across enormous distances. To appreciate how large this pattern is, imagine shrinking the Milky Way galaxy down to the size of a small coin. At that scale, the nearest large galaxy, Andromeda, would be about a few meters away. But the cosmic filaments connecting clusters of galaxies would stretch for hundreds of kilometers across the map, and the voids between them would be even larger. These structures are among the biggest patterns known in nature. Some filaments extend hundreds of millions of light years across. Clusters at the intersections can contain thousands of galaxies, and the voids surrounding them can stretch for hundreds of millions of light years in all directions. If you could somehow travel through the universe and watch this structure from far away, it might look like a glowing web suspended in darkness, thin rivers of galaxies connecting giant nodes of matter, and between them, huge hollow bubbles where galaxies are rare. But how did such a structure form? Why didn't matter simply spread out evenly everywhere? The answer again lies in the early universe. Not long after the universe began, tiny variations in density existed throughout space. Some regions contained slightly more matter, others contained slightly less. The differences were extremely small. If you could measure them, they would be like gentle ripples across a calm lake. But gravity slowly amplified those ripples. Where matter was slightly denser, gravity pulled in more material. Those regions grew into galaxy clusters and filaments. Meanwhile, the slightly emptier regions lost matter as it flowed away toward the denser areas. Those regions expanded into the cosmic voids. Over billions of years, this process created the sponge-like pattern we observe today. The cosmic web is the result of gravity slowly shaping matter across unimaginable distances. And interestingly, this pattern appears not only in galaxy maps, but also in computer simulations. Scientists run enormous simulations that recreate the evolution of the universe using powerful supercomputers. These simulations start with the tiny density ripples seen in the cosmic microwave background. the ancient light left over from the early universe. Then they allow gravity to act on those ripples for billions of years. As the simulation evolves, matter begins clumping together, filaments form, clusters appear, and the empty regions grow larger. When the final simulated universe is compared to real galaxy surveys, the similarity is remarkable. The simulated cosmic web looks almost identical to the one astronomers observe in the real universe. This agreement gives scientists confidence that they understand the basic processes shaping cosmic structure. But the cosmic web is not static. It continues to evolve even today. Gravity still pulls matter towards dense regions. Galaxies slowly drift toward clusters, and the voids continue to grow larger and emptier over time. It's a bit like watching foam expand as bubbles merge and shift. The pattern slowly changes, but the overall structure remains. And as the universe expands, the voids stretch wider. Some may eventually reach sizes far beyond anything we observe today. But perhaps the most fascinating thing about the cosmic sponge is what it tells us about our place in the universe. Our galaxy is just one tiny point along one filament of this enormous web. If the cosmic web were shrunk down to the size of a giant city, the Milky Way might be no larger than a single grain of sand, somewhere along one street. Yet from that tiny location, we are able to observe the entire pattern. We can map the galaxies, study the voids, and slowly uncover the shape of the universe itself. A universe that is not filled solid with matter, but shaped by vast bubbles of emptiness, woven together into one of the largest structures nature has ever created. When we look at the universe today, the pattern seems clear. Galaxies gather in clusters. They stretch along filaments like glowing rivers across space, and between them lie enormous cosmic voids. But this raises a quiet and fascinating question. How did those voids form in the first place? Did something push galaxies away from those regions? Or were they simply born empty? To understand the answer, we need to go back to a time when the universe was very young, not millions of years old, not even thousands, just a few 100,000 years after the beginning of the universe. At that time, the universe was filled with hot gas spread throughout space. There were no stars yet, no galaxies, just a vast ocean of matter and energy. But that ocean was not perfectly smooth. Tiny variations existed everywhere. Some regions had slightly more matter than others. The differences were incredibly small. Imagine a calm lake on a windless day. The surface looks perfectly flat at first glance, but if you look closely, you might see gentle ripples moving across the water. The early universe had similar ripples. These ripples were tiny differences in density. Places where matter was just a little thicker or a little thinner. At the time, those small differences didn't seem important. But gravity notices even the smallest imbalance. Where matter was slightly denser, gravity began pulling additional material toward that region. Over time, that region became even denser, and the more matter gathered there, the stronger the gravitational pull became. It was a slow process, but over billions of years, these slightly dense areas grew into something much larger. They became the seeds of galaxy clusters. Meanwhile, something else was happening to the slightly emptier regions. Because matter was flowing toward the denser areas, the less dense regions gradually lost material. The more matter moved away, the emptier those regions became. And as they became emptier, they began to expand. To picture this process, imagine placing raisins inside rising bread dough. As the dough expands, the raisins move apart. But if the raisins happen to cluster in certain areas, the surrounding regions of dough stretch more and more as the bread rises. The clusters of raisins become denser. The spaces between them become larger. The universe behaves in a similar way. The galaxies are like the raisins. Space itself is like the rising dough. As the universe expands, gravity gathers galaxies into clusters and filaments. Meanwhile, the spaces between those structures stretch into cosmic voids. Another way to imagine it is to think of a crowd of people standing across a large open field. If everyone slowly begins walking toward the densest groups of people, the crowded areas grow thicker, but the regions people leave behind become emptier and emptier. Eventually, large clearings appear where almost no one remains. Cosmic voids form through a similar process. Matter flows away from those regions toward denser structures. The voids are not pushed outward by some force. Instead, they expand because matter leaves them. And once a void begins forming, the process tends to continue. Gravity pulls matter toward the surrounding filaments and clusters. This makes the void even emptier. As it becomes emptier, its internal gravity becomes weaker. That means there is less pull holding material inside, so even more matter drifts away toward the edges. It becomes a kind of cosmic feedback loop. The emptier the region becomes, the faster matter escapes. Over billions of years, this process can create enormous bubbles of emptiness. Some cosmic voids stretch hundreds of millions of light years across. If light began crossing such a void when the first mammals appeared on Earth about 200 million years ago, that light would still not have reached the other side today, and the void would continue growing because the universe itself is expanding. As space stretches, the voids stretch with it. But interestingly, voids do not grow simply by expanding with the universe. They also grow by absorbing smaller voids. When two nearby voids expand, the boundary between them can weaken. Eventually, the smaller wall separating them may dissolve. The two voids merge into one larger bubble. It's similar to what happens when soap bubbles touch. Two small bubbles can merge into one bigger bubble. The same thing can happen with cosmic voids over long periods of time. This merging process helps create the largest voids we observe today. But even the emptiest voids are not completely empty. A few galaxies may remain scattered inside them. Thin gas still drifts through the darkness. And dark matter, the invisible substance that makes up much of the universe's mass, also exists within these regions. Yet compared to the crowded galaxy clusters along the cosmic filaments, voids remain some of the most peaceful and quiet places in the universe. They are vast cosmic deserts, regions where gravity has slowly cleared away most of the material over billions of years. And as the universe continues to age, these voids will likely grow even larger. Galaxies will keep drifting toward clusters. Filaments will become more pronounced, and the cosmic bubbles between them will expand. Over unimaginable stretches of time, the universe may become even more dominated by emptiness. Because once a void begins forming, it rarely stops growing. Cosmic voids are not frozen structures. They are not empty bubbles that formed once long ago and then stayed exactly the same. Instead, they are constantly changing, very slowly, very gently. But over billions of years, those changes become enormous. To understand why voids grow over time, it helps to picture the universe as something that is still expanding. Space itself is stretching in every direction. Galaxies are not simply flying outward like sparks from a firework. Instead, the space between them is slowly getting larger. It's a bit like drawing dots on the surface of a balloon and then inflating it. As the balloon expands, the dots move farther apart, even though they are not sliding across the surface. The universe behaves in a similar way. As space expands, the distances between galaxies slowly increase. But this expansion does not happen evenly everywhere. Gravity still plays a role. Regions that contain lots of matter, such as galaxy clusters, have stronger gravity. They pull galaxies inward toward them. Meanwhile, regions that contain less matter, the cosmic voids, have weaker gravity. There is simply less material there to pull things back. Because of that difference, galaxies near voids tend to drift toward the surrounding filaments and clusters. Matter slowly flows away from the emptier regions. And as this happens, the voids grow larger. Imagine again a crowd of people standing across a large open field. If everyone slowly begins walking toward the areas where people are already gathered, the crowded groups become thicker. Meanwhile, the empty spaces between those groups become wider. After enough time passes, the clearings in the field grow larger and larger. Cosmic voids behave the same way. Matter gradually leaves them. Galaxies slowly drift toward the denser structures along the edges, and the empty region expands. But the growth of voids is not just about matter drifting away. The expansion of the universe itself also plays a role. As space stretches, the voids stretch with it. Think of a bubble rising inside a loaf of bread as it bakes. The dough expands everywhere, but the bubbles inside the bread also expand as the dough rises. The bubbles grow larger, while the bread itself grows. In the same way, cosmic voids grow both because the universe expands and because matter flows away from them. This combination causes voids to become emptier and wider over time. Computer simulations of the universe show this process very clearly. Scientists create virtual universes inside powerful supercomputers. They start with the tiny density variations that existed shortly after the Big Bang. Then they allow gravity to act on those variations over billions of years. As the simulation evolves, galaxies gather into filaments and clusters. Meanwhile, the empty regions expand. Small voids form first, then they merge. Two nearby voids may slowly grow until the thin wall of matter between them disappears. Once that wall collapses, the two smaller voids become one larger void. Over time, this merging process creates the enormous cosmic bubbles astronomers observe today. Some of the largest known voids stretch hundreds of millions of light years across. To picture that distance, imagine light starting its journey across one of these voids. When the first birds evolved from dinosaurs about 150 million years ago, even traveling at the fastest speed possible, that light might only now be reaching the other side. And even today, those voids continue expanding. The galaxies along their edges slowly move farther apart. Clusters become denser as they gather more material, and the voids between them widen. This slow evolution means the universe gradually becomes more structured over time. Early in the universe, matter was spread more evenly. The cosmic web was faint, clusters were smaller, voids were less pronounced. But over billions of years, gravity amplified the differences. Dense regions grew denser, empty regions became emptier. Today, the cosmic web is clearly visible in galaxy surveys. Filaments stretch across enormous distances. Clusters shine with thousands of galaxies, and the voids between them form some of the largest structures in existence. Yet even in these vast empty bubbles, the universe never reaches perfect emptiness. A few galaxies still drift within them. Thin gas floats through the darkness. Dark matter, the invisible mass that helps shape cosmic structures, remains present as well. But compared to the crowded clusters along the cosmic web, voids remain extremely quiet places. Galaxies inside them are rare. Encounters between galaxies are uncommon, and the sky between distant galaxies stretches farther than in most regions of space. In many ways, voids are the calmest parts of the universe, but their growth tells an important story. They reveal how gravity and cosmic expansion shape the large-scale structure of the universe. Over time, the universe becomes more and more like a foam of galaxies and empty bubbles. And as that foam evolves, some galaxies find themselves drifting into very unusual neighborhoods, galaxies that live far from clusters, far from filaments, far from almost everything. Some of these galaxies are so isolated that their nearest large neighbor may lie tens of millions of light years away. They are the loneliest galaxies in the universe, and studying them reveals something remarkable about life inside cosmic voids. When people imagine cosmic voids, they often picture completely empty space, a vast region where nothing exists at all. But the universe rarely leaves anything perfectly empty. Even inside the largest voids, a few galaxies still exist. These galaxies are extremely rare compared to those in crowded clusters, but they are there, drifting quietly through the darkness. And because they live in such unusual environments, these galaxies behave differently from many of their cousins in denser parts of the universe. To understand why, it helps to imagine two very different cities. One city is crowded and busy. Skyscrapers fill the skyline. Roads are packed with traffic, and people constantly interact with each other. The other city is small and remote. Only a few buildings stand across a wide open landscape. The nearest town might be hours away. Life in those two places would feel very different. Galaxies experience something similar, depending on where they live in the cosmic web. In crowded regions of the universe, galaxies are constantly interacting. They pass close to one another, pull on each other with gravity, and sometimes collide. When galaxies collide, enormous clouds of gas inside them crash together, triggering bursts of star formation. Imagine two weather systems colliding in Earth's atmosphere, creating powerful storms. Galactic collisions can produce something similar, sudden bursts of new stars lighting up the galaxy. But inside cosmic voids, those interactions are rare. Galaxies are so far apart that they may drift for billions of years without ever encountering another large galaxy. To picture that distance, imagine driving across Earth from one side to the other. Even that long journey covers only about 13,000 kilometers. Now imagine repeating that trip millions of times before reaching the next galaxy. That is the kind of separation some void galaxies experience. Because of this isolation, galaxies inside voids often evolve more slowly. Without frequent collisions, their shapes remain more stable. Their gas clouds form stars gradually instead of in dramatic bursts. Many void galaxies are spiral galaxies, with gentle arms of stars winding around their centers. These spirals can remain relatively undisturbed for long periods. In contrast, galaxies inside crowded clusters are often distorted by gravitational interactions. Some are stretched or warped, others merge together, forming giant elliptical galaxies. But void galaxies often avoid that chaotic environment. They live quieter lives. Another interesting feature of many void galaxies is that they still contain plenty of gas. Gas is the raw material for forming new stars. In dense regions, galaxies sometimes lose much of their gas through interactions with nearby galaxies or the hot gas-filling galaxy clusters. Inside voids, however, galaxies may hold on to their gas for much longer. That means they can continue forming stars steadily for billions of years. In some cases, void galaxies may still be building new stars, while similar galaxies in clusters have already slowed down. Studying these isolated galaxies helps astronomers answer important questions. How do galaxies grow when left alone? What happens when they evolve without constant gravitational disturbances? Void galaxies provide a natural laboratory for exploring those questions. But the loneliness of these galaxies can be extreme. Some are separated from their nearest neighbors by tens of millions of light years. To understand that scale, remember that the nearest large galaxy to the Milky Way, Andromeda, lies about 2.5 million light years away. That already feels incredibly distant. Now imagine a galaxy whose nearest major neighbor is 10 times farther away than that, or even 20 times farther. Such galaxies exist inside large cosmic voids. They drift through enormous regions of space, where the night sky between galaxies is darker than in most parts of the universe. Yet even in these quiet environments, gravity still shapes their motion. Galaxies inside voids slowly drift toward the edges of the void. This happens because the surrounding filaments and clusters contain more matter. Gravity gently pulls galaxies in that direction. Over billions of years, many galaxies may gradually migrate toward the boundaries of the void. The process is slow, extremely slow, but the overall effect helps keep the centers of voids relatively empty. Some astronomers even describe this motion as galaxies falling out of the void. It's not a sudden fall like dropping an object on Earth. Instead, it's more like drifting slowly down a gentle slope over immense stretches of time. And as galaxies slowly move towards the edges, the void becomes even emptier. But even though galaxies inside voids are rare, they are important. By studying them, astronomers learn how galaxies behave in isolation. They help reveal what a galaxy might look like if it grew up far from crowded clusters. In many ways, these galaxies are like quiet islands scattered across a vast cosmic ocean, each one shining with billions of stars, each one drifting through darkness that stretches across unimaginable distances. And among them are some of the most isolated galaxies ever discovered. Galaxies so lonely that their nearest companions lie almost unimaginably far away. These are often called the loneliest galaxies in the universe. And their quiet existence offers a glimpse into what life might be like deep inside the universe's greatest cosmic voids. Some galaxies live in busy neighborhoods. In large galaxy clusters, hundreds or even thousands of galaxies gather together in a relatively small region of space. These clusters can be packed into areas only a few million light-years across. To imagine that distance, remember that the Milky Way is about 100,000 light-years wide. A galaxy cluster, a few million light-years across, would still be large enough to place the Milky Way 20 or 30 times side by side. Inside those clusters, galaxies are constantly interacting. They pass near each other, stretch each other with gravity, and sometimes merge together. It can be a chaotic environment, but far away from those busy regions are galaxies that live almost entirely alone. These are the loneliest galaxies in the universe. They are found deep inside cosmic voids, where the distances between galaxies can become enormous. In some cases, the nearest large neighbor may lie tens of millions of light-years away. To understand just how isolated that is, it helps to compare it with our own galaxy's surroundings. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, about 2.5 million light-years away. Even that distance feels enormous. If light left Andromeda tonight, it would not reach Earth for 2.5 million years. But some void galaxies have no major neighbor within 20 or even 30 million light-years. That is like moving from a town where the nearest city is a short drive away to a place where the nearest city is on another continent. In cosmic terms, these galaxies are extremely isolated. Astronomers sometimes call them field galaxies, meaning they exist far from clusters or dense filaments of the cosmic web. But the ones deep inside, voids take isolation to another level. One famous example is a galaxy called MCG plus 0102015. This galaxy lies in a region so empty that its nearest significant neighbor is about 100 million light-years away. To picture that distance, imagine light starting its journey across that gap. When the first dinosaurs appeared roughly 230 million years ago, even today, that light would not yet have reached the other galaxy. That is the scale of separation involved. Galaxies like this drift through immense stretches of darkness, with almost no nearby companions. Their sky would look very different from the sky seen in crowded parts of the universe. From within such a galaxy, astronomers looking outward with powerful telescopes might find only a few distant galaxies scattered across the sky. Instead of seeing many clusters and filaments nearby, they might observe vast regions where galaxies are extremely sparse. The cosmic landscape would feel wide and quiet. But even though these galaxies are lonely, they are still fascinating places. Because they evolve in isolation, they provide astronomers with an opportunity to study how galaxies behave without outside influence. In crowded regions, galaxies constantly disturb each other. Gravity stretches their shapes, pulls gas away, and triggers bursts of star formation. Inside voids, those disturbances are rare. Galaxies may keep their original structures for much longer, Some remain beautiful spiral galaxies with well-defined arms, gently rotating around their centers. Others continue forming stars steadily for billions of years. Their evolution is quieter and more gradual. In many ways, these galaxies are like remote villages that grow slowly over time without the rapid changes seen in busy cities. Studying them helps astronomers understand the natural life cycle of galaxies when they are left mostly alone. But even the loneliest galaxies are not completely disconnected from the universe. Gravity still acts on them. The surrounding cosmic web still influences their motion. Over incredibly long periods of time, some of these galaxies may slowly drift toward the edges of the void, where more matter exists. The process is extremely slow. It might take billions of years for a galaxy to move significantly closer to a filament or cluster. But over cosmic time, even these isolated islands slowly migrate within the structure of the universe. Another interesting feature of void galaxies is their dark matter halos. Every galaxy is surrounded by an invisible halo of dark matter, the mysterious substance that makes up most of the universe's mass. Dark matter does not emit light, but its gravity helps hold galaxies together. Even inside cosmic voids, dark matter still exists. In fact, the distribution of dark matter plays an important role in shaping the boundaries of voids. Where dark matter is slightly denser, galaxies are more likely to form. Where it is thinner, large empty regions appear. So even though voids may seem empty at first glance, their structure is still guided by this invisible framework. And this raises an interesting thought. When we look at the cosmic web, we often focus on the galaxies because they shine with visible light, but much of the universe's structure is actually shaped by something we cannot see at all. Dark matter. It forms the invisible scaffolding of the cosmic web, and even the emptiest voids still contain traces of it, quietly shaping the boundaries of the largest bubbles in the universe. When astronomers map the universe, the galaxies are the easiest things to see. Each galaxy shines with billions of stars, glowing across millions of light years of space. Through telescopes, these galaxies appear like tiny islands of light, scattered across the darkness. But what we see is only part of the story. In fact, most of the universe is made of something invisible, something that does not shine, does not reflect light, and cannot be seen directly with any telescope. Scientists call it dark matter. Dark matter is one of the greatest mysteries in modern science. Even though we cannot see it, we know it exists because of its gravity. Galaxies behave as if they contain far more mass than we can observe. For example, when astronomers measure how quickly stars orbit the centers of galaxies, they find something surprising. The outer stars move much faster than expected. If galaxies contained only the visible matter we see, stars, gas, and dust, those outer stars should drift away into space. Instead, they remain bound to the galaxy. Something unseen is holding them in place. That something is dark matter. Dark matter forms enormous halos surrounding galaxies, extending far beyond the visible stars. If the Milky Way stars form a bright disk about 100,000 light-years wide, the dark matter halo around it may stretch several 100,000 light-years across. That is like placing a glowing city at the center of a vast invisible landscape. But dark matter does more than surround individual galaxies. It also shapes the large-scale structure of the universe. Long before galaxies formed, dark matter was already gathering into clumps and filaments. Under the pull of gravity, these structures acted like a kind of cosmic scaffolding. Ordinary matter, the atoms that form stars and galaxies, later fell into these dark matter structures. Where dark matter was dense, galaxies formed. Where dark matter was sparse, fewer galaxies appeared. This invisible framework helped create the cosmic web we observe today. The filaments of galaxies follow the underlying filaments of dark matter. Clusters of galaxies sit in regions where dark matter concentrations are strongest, and the cosmic voids appear where dark matter is least abundant. But even inside voids, dark matter does not disappear completely. There is still some present, just much less of it. Imagine a large sponge floating in water. Some parts of the sponge contain thicker material, while the holes contain mostly water. Dark matter behaves in a similar way. It fills the universe, but its density changes from place to place. The filaments contain more, the voids contain less, but they are never perfectly empty. Computer simulations of the universe help scientists visualize this invisible structure. In these simulations, researchers create vast digital universes filled with dark matter particles. They allow gravity to act on those particles for billions of years. As the simulation evolves, dark matter slowly gathers into long filaments and dense clusters. Between those structures, large empty regions appear. When scientists add normal matter to the simulation, the matter that forms stars and galaxies, it naturally flows into the same dark matter structures. The galaxies form along the filaments and clusters, and the voids remain mostly empty. When these simulated universes are compared to real galaxy surveys, the resemblance is striking. The patterns match remarkably well. This agreement strongly suggests that dark matter plays a crucial role in shaping the cosmic web. Even though we cannot see dark matter directly, its gravitational influence leaves a clear fingerprint across the universe. But dark matter also influences how cosmic voids behave. Because voids contain less dark matter than surrounding regions, their gravitational pull is weaker. That means matter near the edges of voids is more easily pulled toward nearby filaments and clusters. Over time, this process helps the void expand. The boundaries of the void slowly push outward as galaxies drift towards denser areas. In a way, dark matter helps define the walls of the cosmic bubbles. Where dark matter gathers, galaxies follow. Where it is sparse, vast empty regions form. But here is something interesting. Even though voids contain less dark matter, they can still reveal important clues about it. By studying how galaxies move near the edges of voids, astronomers can measure the gravitational influence of the dark matter surrounding them. These measurements help scientists test theories about how dark matter behaves. In some cases, the shapes of voids themselves provide hints about the underlying dark matter structure. It is a bit like studying the shape of waves on the ocean to understand the currents beneath the surface. The waves reveal patterns that are otherwise invisible. In the same way, cosmic voids reveal the hidden distribution of dark matter across the universe. And even though voids may appear almost empty, they still contain traces of matter. Thin gas drifts through the darkness. A few lonely galaxies float across vast distances, and dark matter quietly shapes the boundaries of these giant bubbles. But just how empty are cosmic voids? Really, if we could somehow travel deep into one of these regions, would we find absolute nothingness? Or would there still be something there, quietly filling the darkness? The answer turns out to be surprisingly interesting, because even the emptiest places in the universe are never truly empty. When people hear the word void, it often brings to mind a place where absolutely nothing exists. A region of perfect emptiness. No stars, no galaxies, no matter at all. But in the universe, perfect emptiness is almost impossible to find. Even the quietest regions of space still contain something. Cosmic voids are extremely empty compared to other parts of the universe. But they are not completely empty. They still contain small amounts of matter, just spread incredibly thin. To understand how thin, imagine the air around you right now. Even though air looks invisible, it actually contains trillions upon trillions of molecules moving around. If you could scoop up a small box of air the size of a shoebox, it would still contain more molecules than there are grains of sand on an entire beach. Space is very different. In the space between stars inside our galaxy, there might be only a few atoms in a space as large as a room. That is already incredibly empty compared to the air we breathe. But inside cosmic voids, the density can be even lower. In some regions, there may be only a few atoms in a volume the size of a small house. Imagine an enormous building the size of a sports stadium. Now imagine that entire space, containing only a handful of particles, drifting slowly through it. That is the level of emptiness inside many cosmic voids. Yet even there, matter still exists. Thin gas floats through the darkness. Dark matter remains present, quietly shaping the gravitational landscape. And scattered across these vast regions are a few isolated galaxies. These galaxies may be separated by tens of millions of light years. To picture that distance, imagine the Milky Way galaxy shrunk down to the size of a small coin. On that same scale, another galaxy inside the void might be placed hundreds of kilometers away. They are incredibly far apart, but they still exist. Because the universe rarely leaves anything completely empty. Even in the emptiest regions, gravity, gas, and dark matter still play a role. Interestingly, scientists can detect the faint gas inside cosmic voids by studying how light travels through space. When light from a distant quasar, an extremely bright galaxy powered by a supermassive black hole, travels toward Earth, it passes through clouds of gas along the way. Each cloud leaves tiny fingerprints in the light spectrum. By studying these fingerprints, astronomers can measure how much gas exists between us and the quasar. These measurements reveal that even inside voids, extremely thin gas still drifts through space. This gas is often made of simple elements like hydrogen, the most common element in the universe. Although the gas is extremely sparse, it still fills the void in a faint, almost invisible way. It is more like a gentle mist than a dense cloud. Another interesting discovery is that some voids contain faint structures known as void filaments. These are very thin strands of matter that stretch across the emptiest regions. They are far weaker than the main filaments of the cosmic web, but they still exist. Occasionally, a few small galaxies may form along these faint strands. These galaxies are usually small and isolated, but they show that even in the emptiest parts of the universe, structure can still appear. And then there is dark matter. Even though we cannot see it directly, dark matter is thought to exist almost everywhere in the universe. Inside voids, the density of dark matter is much lower than in galaxy clusters, but it is not completely absent. Simulations of the universe show that voids still contain faint traces of dark matter, forming subtle structures. These structures influence how galaxies move and how the boundaries of voids evolve. So while cosmic voids are incredibly empty compared to most of the universe, they are not perfect vacuums. They are more like enormous cosmic deserts. In a desert on Earth, life is rare, water is scarce, and vast stretches of land may appear empty, but life still exists there. Plants grow in scattered places, animals travel across the dunes, wind moves grains of sand slowly across the landscape. Cosmic voids are similar. Galaxies are rare, matter is spread extremely thin, but the universe still fills these regions with faint traces of gas, dark matter, and occasional lonely galaxies. And even though voids are quiet places, they can still influence the universe in important ways. Some scientists believe that the presence of large voids could affect how we measure the expansion of the universe. Because if we happen to live inside a region with slightly less matter than average, it might change how we observe distant galaxies moving away from us. This possibility connects to one of the most puzzling mysteries in modern astronomy. A puzzle involving two different ways of measuring the expansion rate of the universe. Both methods are extremely precise. Both are supported by strong evidence, yet their answers do not quite match. This mystery has become known as the Hubble tension, and some researchers have wondered whether cosmic voids might play a role in explaining it. One of the most important discoveries in modern astronomy is that the universe is expanding. Galaxies are not standing still in space. Instead, the distances between them are slowly increasing as space itself stretches. This idea was first confirmed in the early 1900s, when astronomers noticed that distant galaxies appear to be moving away from us. The farther away a galaxy is, the faster it seems to recede. To picture this, imagine drawing several dots on the surface of a balloon. If you slowly inflate the balloon, the dots move farther apart as the surface stretches. The dots are not sliding across the balloon. The balloon itself is expanding. The universe behaves in a similar way. Galaxies are like the dots. Space is like the surface of the balloon. As the universe expands, galaxies move farther apart. Astronomers measure this expansion using a value called the Hubble constant. This number describes how fast galaxies appear to move away, depending on their distance. For example, if one galaxy is twice as far away as another, it should appear to move away roughly twice as fast. But measuring the Hubble constant is not as simple as it might sound. The universe is extremely large, and our observations come from one specific location. Here on Earth, inside the Milky Way galaxy. That means every measurement we make depends on the environment around us. And that raises an interesting question. What if our part of the universe is not perfectly average? What if the region around our galaxy contains slightly less matter than most places? In other words, what if we are living inside a cosmic void? If that were the case, it might slightly affect how we measure the expansion of the universe. To understand why, imagine standing inside a large valley surrounded by hills. If rainwater flows across the land, it tends to move downhill toward the lowest areas. From inside the valley, the flow of water might appear stronger compared to what someone standing on a flat plain would observe. In the universe, matter flows in a somewhat similar way. Gravity pulls galaxies toward dense regions like clusters and filaments. Meanwhile, regions with less matter, cosmic voids, slowly expand as material drifts away. If our galaxy were located inside such a region, nearby galaxies might appear to move away slightly faster than expected. From our perspective, it could look as if the universe is expanding more quickly in our local area. That difference might influence how we calculate the Hubble constant. It would be similar to measuring the speed of cars while standing on a downhill slope. Cars might appear to move faster there than they do on level ground, even though the highway itself follows the same rules everywhere. Some scientists have explored this idea using computer models of the universe. They simulate what the universe would look like if our galaxy were located inside a large, underdense region. In these models, galaxies near the edges of the void gradually drift outward. Observers inside the void might see surrounding galaxies moving away slightly faster. This could potentially raise the measured expansion rate in local observations. However, there is still debate about whether this effect would be large enough to explain the differences astronomers observe. Many studies suggest that the void would need to be extremely large, possibly hundreds of millions or even billions of light years across, to create a noticeable change. Some structures, like the proposed KBC void, approach those sizes, but scientists are still studying whether such a void truly surrounds our galaxy. Another complication is that the universe contains many voids of different sizes. Galaxies near the edges of these voids may experience small gravitational influences from nearby structures. These local effects can make measurements slightly more complicated. Despite these challenges, the idea remains interesting because it reminds us of something important. Our view of the universe comes from a single location. We observe the cosmos from one small corner of a vast cosmic web. If that corner happens to lie inside a slightly unusual region, it might influence what we see. But even if cosmic voids contribute to small measurement differences, they are unlikely to change the overall picture. The universe is still expanding, galaxies are still drifting apart over time, and the cosmic web continues evolving as matter flows towards dense structures and away from emptier regions. Yet the possibility that our local environment might subtly influence our measurements shows how carefully astronomers must interpret their observations. Even the largest cosmic measurements can depend on where you happen to stand in the universe. And this brings us to one of the most intriguing puzzles in modern cosmology. Two different methods of measuring the universe's expansion rate give slightly different answers. One method studies nearby galaxies and exploding stars. The other studies the ancient light left over from the early universe. Both methods are extremely precise. Both are supported by strong evidence, yet their results do not quite agree. This disagreement has become one of the biggest open questions in astronomy today, and some scientists wonder whether the answer might lie in the large-scale structure of the universe itself. Astronomy is full of mysteries, but sometimes the most interesting ones come from numbers that almost match. Almost. Scientists have developed several ways to measure how fast the universe is expanding. Each method is based on careful observations and years of research. Yet, when the results are compared, something unexpected appears. The numbers do not quite agree. This disagreement has become known as the Hubble tension. To understand why this matters, it helps to know how astronomers measure the expansion of the universe. One method looks at the early universe. Astronomers study the ancient light left over from shortly after the universe began, the cosmic microwave background. This faint glow has been traveling through space for about 13.8 billion years. By carefully studying tiny temperature patterns in that light, scientists can calculate how the universe should expand over time. Using this method, researchers estimate the expansion rate to be about 67 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light years. So this number means that for every 3.26 million light years of distance, a galaxy appears to move away about 67 kilometers per second faster. Now imagine measuring the expansion in a different way. Instead of studying the early universe, astronomers can measure nearby galaxies directly. They observe certain types of exploding stars, called Type Ia supernovae. These explosions shine with very predictable brightness, which allows scientists to measure their distance with remarkable accuracy. By comparing the distances to these supernovae with how fast their galaxies are moving away, astronomers can calculate the expansion rate. This method gives a slightly different result, about 73 kilometers per second per megaparsec. The difference may not sound large. It's only about 6 kilometers per second. But in cosmology, even small differences matter. Imagine two extremely precise clocks that should show exactly the same time. If one clock reads 12 o'clock and the other reads 12:03, that small difference tells you something in the system might not be fully understood. The Hubble tension is similar. Two highly reliable methods produce slightly different answers. So scientists are asking an important question. Why? Several possibilities exist. One idea is that there may be new physics we have not yet discovered. Perhaps dark energy, the mysterious force driving cosmic expansion, behaves slightly differently than expected. Or perhaps dark matter interacts with the universe in ways we do not yet understand. But another possibility involves something simpler, our local environment. If the Milky Way happens to sit inside a large cosmic void, it might influence the way we measure the expansion of nearby galaxies. To picture this, imagine standing inside a wide valley surrounded by hills. If you release a ball on the ground, it may naturally roll outward toward the slopes. From inside the valley, it might appear that objects move away faster than they would on flat ground. Cosmic voids behave somewhat like that valley. Because voids contain less matter, their gravity is weaker. Galaxies near the edges slowly drift outward toward denser regions. If we live inside such a region, nearby galaxies might appear to move away slightly faster than average. That effect could increase the expansion rate measured from nearby observations. Meanwhile, measurements based on the early universe would not be affected by our local environment. Those measurements describe the universe on the largest scales. This difference between local and global measurements could help explain the Hubble tension. Some scientists have explored this idea using computer simulations. In these simulations, They place an observer inside a large underdense region and measure how galaxies would appear to move. In certain cases, the expansion rate measured locally does increase slightly. However, there is a challenge. To explain the entire Hubble tension, the void surrounding our galaxy would need to be extremely large, possibly hundreds of millions of light years across, or even close to 1 billion light years wide. Structures of that size do exist in the universe, but astronomers are still debating whether such a massive void surrounds the Milky Way. Some studies suggest our region of space may indeed contain fewer galaxies than average. Other studies find that the difference may not be large enough to fully solve the puzzle. The answer is still uncertain, and that uncertainty keeps the mystery alive. But regardless of the final explanation, the discussion highlights something fascinating. The universe is not perfectly uniform. It contains enormous structures, clusters, filaments, and voids, stretching across unimaginable distances. These structures can influence how galaxies move and how we observe the cosmos. And sometimes, the biggest clues about the universe come from studying its emptiest regions, because cosmic voids are not just gaps between galaxies. They are some of the largest structures ever discovered. In fact, when astronomers rank the biggest known structures in existence, cosmic voids stand alongside enormous galaxy clusters and superclusters, structures so vast that light itself may take hundreds of millions of years just to cross them. When people imagine the largest objects in the universe, they often think of galaxies. A single galaxy like the Milky Way already feels enormous. It contains hundreds of billions of stars and stretches about 100,000 light-years across. Even traveling at the speed of light, it would take 100,000 years to cross from one side of the galaxy to the other. That alone is difficult to imagine. But galaxies are only the beginning. Galaxies gather together into groups and clusters. The Milky Way, for example, belongs to a small collection of galaxies called the Local Group, which contains about 50 galaxies spread across roughly 10 million light-years. That means, if light left one edge of the Local Group, it would take 10 million years to reach the other side. Yet even that structure is small compared to what lies beyond. Clusters of galaxies gather into even larger structures, known as superclusters. Our Local Group sits near the edge of a massive structure called the Virgo supercluster, which stretches for about 110 million light-years. To picture that size, imagine light starting its journey across this region when the first dinosaurs appeared roughly 230 million years ago. Even today, that light might still be traveling across the structure. But even superclusters are not the largest patterns in the universe. When astronomers map galaxies across billions of light-years, they see something even more impressive. The cosmic web. Long filaments of galaxies stretch across space like glowing threads. At the intersections of these filaments, enormous galaxy clusters gather. Between them lie the cosmic voids. These voids are not simply empty gaps, they are enormous structures themselves. In fact, many cosmic voids are hundreds of millions of light-years across. Some may approach 1 billion light-years wide. To picture that distance, imagine shrinking the Milky Way galaxy down to the size of a small coin. At that scale, a void 1 billion light-years across would be larger than an entire country. You could scatter thousands of Milky Way-sized galaxies across that space and still leave vast regions empty. This means that some of the largest structures in the universe are not made of matter at all. They are made of absence, enormous bubbles where galaxies are extremely rare. These voids help define the shape of the cosmic web. The filaments and clusters appear where matter gathers. The voids appear where matter has drifted away. Together they create the sponge-like pattern stretching across the observable universe. And this pattern repeats on the largest scales we can observe. If astronomers zoom out far enough, the cosmic web becomes visible across billions of light-years. Huge chains of galaxies connect massive clusters. Between them, Vast voids stretch across space. Some of these voids may rival the largest galaxy clusters in size. For example, the Boötes void is about 330 million light-years across. The Eridanus supervoid may approach 1 billion light-years in diameter, and the proposed KBC void surrounding our galaxy may extend nearly 2 billion light-years. These distances are so vast that they challenge our ability to imagine them. If light began crossing a 2 billion light-year wide region when the first dinosaurs appeared on Earth, it would still be traveling today. Even now, it would have more than 8 times the age of human civilization left to go before reaching the other side. That is the scale of the largest cosmic structures. But interestingly, when astronomers study the universe on the very largest scales, beyond several billion light-years, something remarkable appears. The universe begins to look more uniform again. The cosmic web exists on enormous scales, but if we zoom out far enough, the overall distribution of matter becomes smoother. This idea is known as the cosmological principle. It suggests that while the universe contains large structures like clusters and voids, the overall average distribution of matter is roughly the same in all directions when viewed across sufficiently large distances. In other words, the universe is lumpy up close, but smooth on the grandest scales. A good comparison is the surface of the Earth. If you stand in a valley or on a mountain, the landscape appears uneven and dramatic. But if you look at Earth from space, the planet appears smooth and round. The mountains and valleys are tiny details compared to the size of the entire planet. The universe behaves in a similar way. Clusters, filaments, and voids create dramatic structure across hundreds of millions of light-years. But across billions of light-years, the average distribution becomes more uniform. Still, within that grand cosmic landscape, the voids remain some of the most impressive features. They are giant bubbles carved into the fabric of the universe, and their size raises an intriguing thought. If some voids are large enough to span hundreds of millions, or even billions of light-years, could our own galaxy be sitting deep inside one right now? If that were true, it might slightly change the way the universe looks from our perspective. It might subtly influence the measurements we make. And it might mean that our cosmic neighborhood is quieter and emptier than the average region of the universe. A possibility that leads to one final question. What if our galaxy truly is inside a giant cosmic void? After exploring the vast cosmic web, the giant bubbles of emptiness, and the lonely galaxies drifting inside them, a quiet question naturally returns. What if our own galaxy is inside one of these enormous voids? Not just near one, but truly inside it. From our everyday view of the night sky, this idea might seem unlikely. The stars above us appear countless and bright. The Milky Way stretches across the sky like a river of light. But almost everything we see belongs to our own galaxy. The Milky Way contains hundreds of billions of stars, spread across a disk about 100,000 light-years wide. Those stars fill our sky simply because we are living inside the galaxy itself. But compared to the vast distances between galaxies, the Milky Way is only a tiny island. Beyond it lies a universe where galaxies are separated by millions of light-years, and the cosmic web, the network of filaments, clusters, and voids, stretches across distances so large that light takes hundreds of millions of years to travel between structures. If our galaxy were located inside a cosmic void, the nearest dense clusters might lie far away along the edges of that enormous bubble. And in fact, some observations hint that our region of space may be slightly less crowded than average. When astronomers map galaxies in the nearby universe, they find that galaxy density increases gradually as they look farther from the Milky Way. Closer regions appear slightly underfilled. Farther regions appear more crowded. This pattern led some scientists to suggest the existence of a large structure called the KBC void, named after the astronomers who studied it. If this void truly exists as proposed, it could stretch nearly 2 billion light-years across. To picture that distance, Imagine light beginning its journey across the void when the first mammals were evolving on Earth about 200 million years ago. Even today, that light would still have a long journey ahead before reaching the other side. That is the scale of the possible structure surrounding us. If we really do sit inside such a region, it would mean our galaxy is located inside one of the universe's enormous bubbles. But would that change how the universe looks to us? In many ways, probably not. Our night sky would still be filled with stars from the Milky Way. Nearby galaxies like Andromeda would still appear in our telescopes. The cosmic microwave background, the ancient light from the early universe, would still surround us from every direction. Yet subtle differences might appear in the large-scale structure of galaxies around us. If our galaxy sits inside a slightly underdense region, nearby galaxies might appear more spread out than the cosmic average. The nearest major clusters might lie farther away, and measurements of how galaxies move might show slight variations compared to what observers in denser regions would see. These effects would be small. The universe is so vast that even large voids occupy only a fraction of the total cosmic volume. But even small differences can matter when scientists measure the universe with incredible precision. For example, if we happen to live in a slightly emptier region of space, nearby galaxies might appear to move away from us a bit faster. This could influence our measurements of the universe's expansion rate. It might contribute, at least partially, to puzzles like the Hubble tension. But whether our galaxy truly sits inside a giant void remains an open question. Some studies support the idea. Others suggest the difference in galaxy density may be smaller than originally thought. Mapping the universe on these scales is incredibly challenging. Even the largest galaxy surveys still observe only a fraction of the total cosmos. It is a bit like trying to map an entire forest while standing inside it. You can see nearby trees clearly, but understanding the full shape of the forest requires stepping far enough away to see the whole landscape. And stepping that far away in astronomy means observing galaxies billions of light years away. As telescopes improve and new surveys map more galaxies, scientists will continue refining our understanding of the cosmic web. They will measure galaxy positions more precisely. They will trace the boundaries of voids more clearly. And slowly, the picture of our cosmic neighborhood will become sharper. But regardless of whether we live inside a giant void or simply near one, the larger truth remains remarkable. The universe is not a uniform ocean of galaxies. It is a vast foam, a structure where matter gathers along thin filaments stretching across unimaginable distances. And between those filaments lie enormous bubbles of emptiness, voids that span hundreds of millions of light years. Voids where galaxies drift alone across enormous darkness. Voids that quietly shape the largest structures in the universe. And when we zoom out far enough, the most surprising realization appears. Some of the biggest structures in the cosmos are not made of galaxies at all. They are made of almost nothing. Which brings us to the final and perhaps most astonishing perspective of all. The realization that the universe itself may be built less from matter and more from the vast spaces where matter is missing. When we first look at the night sky, the universe feels full. Stars shine everywhere. The Milky Way stretches across the darkness like a glowing river. Through telescopes, distant galaxies appear scattered across space like countless islands of light. At first glance, it feels as though the universe must be crowded with matter. But when astronomers step back and look at the cosmos on its largest scales, a very different picture appears. The universe is not packed solid with galaxies. Instead, it is shaped by vast regions where galaxies are rare. Enormous cosmic voids. These voids form the giant bubbles of the cosmic web. Between them lie the filaments and clusters, where galaxies gather, but the emptiness itself dominates the volume of the universe. In fact, scientists estimate that cosmic voids may fill more than 80% of the universe's space. Imagine a giant block of Swiss cheese sitting on a table. The solid cheese represents the galaxies, clusters, and filaments. The holes represent the cosmic voids. Most of the block is actually made of holes. The solid parts simply outline their shapes. The universe works in a similar way. The galaxies mark the boundaries of the enormous empty bubbles, and those bubbles stretch across distances so large they challenge the limits of imagination. Some voids measure hundreds of millions of light years across. Others may approach 1 billion light years wide. And if the proposed KBC void surrounding our galaxy is real, it may span nearly 2 billion light years. To picture that distance, imagine light beginning its journey across such a region. When the first animals began walking on land around 400 million years ago, even today, that light would still be traveling across the void. That is the scale of the emptiness that helps shape the universe. And yet, even inside these enormous bubbles, the universe never reaches perfect nothingness. A few galaxies drift through the darkness. Thin gas floats between them. Dark matter quietly forms the invisible framework guiding the structure of the cosmic web. But compared to the dense clusters along the filaments, voids remain some of the quietest places in the cosmos. They are cosmic deserts, stretching across unimaginable distances. Yet those deserts are not just empty gaps, they are part of the architecture of the universe itself. Without them, the cosmic web would not exist. The filaments of galaxies are defined by the voids surrounding them. The clusters form at the intersections of those filaments. Together, they create a pattern that resembles foam, sponge, or soap bubbles pressed together across billions of light years. This structure grew slowly over time. Shortly after the universe began, matter was spread almost evenly, but tiny ripples in density existed, regions with slightly more matter and regions with slightly less. Gravity slowly amplified those differences. Dense regions gathered more material. Empty regions lost it. Over billions of years, the filaments became denser, the clusters became larger, and the voids became wider and emptier. The cosmic web slowly emerged from those early ripples. Today, that web stretches across the observable universe, galaxies glowing along thin strands, clusters shining with thousands of galaxies, and enormous bubbles of emptiness filling the spaces between them. From our position inside the Milky Way, we occupy only a tiny point along one of those strands. If the entire observable universe were shrunk down to the size of Earth, our galaxy would be smaller than a single grain of sand somewhere on its surface. Yet from that tiny location, we have been able to map the vast structure surrounding us. We have discovered the cosmic web. We have traced the giant voids. We have measured the ancient light from the beginning of time. And we have begun to understand that the universe is not simply a collection of galaxies scattered randomly through space. It is a grand pattern shaped by gravity, time, and expansion, a structure where emptiness plays as important a role as matter. And perhaps that is the most astonishing realization of all. The largest structures in the universe are not galaxies. They are not clusters. They are not even superclusters. They are the enormous spaces between them, the giant cosmic bubbles where almost nothing exists, voids stretching across hundreds of millions of light years, quiet regions where galaxies are rare and darkness dominates the sky. These voids shape the cosmic landscape. They guide the growth of filaments and clusters. They influence how galaxies move across the universe, and they remind us that the universe is far stranger and more beautiful than it first appears. Because when we look deeply enough into the cosmos, we discover something unexpected. The universe is not mostly made of things. It is mostly made of space. Vast, quiet, expanding space. And within that immense ocean of darkness, the galaxies we see are only tiny islands of light, scattered along the edges of the greatest structures ever formed. Structures made not of matter, but of almost nothing at all.